Thanks very much again for having me. Hopefully all of you will find the sort of information that I have to tell you about some of the latest work in fusion interesting. So yes, I actually work in the communications team as the outreach manager for UKAEA. I've been here for almost 5 years now, doing various talks and site visits for various people, from members of the public and schools and university groups, and actually in fact some policy groups and other sort of key stakeholders that want to learn more about us. And so I hope to be able to give a good overview of some of the sort of basics of fusion for those that are unfamiliar with it, and then go and give you a little bit of a look at some of the different projects that we're working at the UK Atomic Energy Authority, or UKAEA. We are the national fusion lab for the UK. And really all of our different research areas are focused on bringing this new sustainable energy source onto the grid in the sort of medium-term future. So let's kind of kick off, really. So I don't think it really takes much imagination for all of us to realize that there is very much a need for a growing number of sustainable energy sources, largely because of climate change. The biggest contributor to this is the burning of fossil fuels and resulting in the mass change and destruction of habitats. And so therefore we're really keen to try and find ways that we can reduce our reliance on fission, on fossil fuels in the future. And see what alternative technologies we can use to fill that gap that will come from reducing global fossil fuels. But alongside the issue of climate change, even if they weren't bad for the environment, they are finite. So it's predicted that there's only about another 100 years left of the world's coal reserves. And so this is kind of just a double whammy for why, for that kind of securing the long-term energy future, we need to be thinking now about new long-term ways to solve a potential looming energy crisis that we may face. And this really kind of like leads nicely on to the idea of the energy mix, the idea that actually we have several different sources of energy, and they all make up varying proportions. But as you can see from the graph, a big contributor that we want to get rid of will still play a relatively large part even into the short-term future, and we want to increase the use of renewables and nuclear, but by themselves we do not believe that they're going to be enough, and they even come with their own drawbacks. I mean, renewables are not 100% reliable, it's not always sunny, and the wind is not always blowing strong enough for us to get enough energy from wind power. And with the current nuclear technology that we have in the form of fission, this, while we can bring it on and turn it on for demand whenever we might need it, it does come with a disadvantage of producing a large amount of radioactive waste that remains radioactive for thousands and tens of thousands of years, producing a secondary, a much longer term issue. But we really believe that fusion will be able to help us fill that gap in that kind of medium to long-term future, and give us what we term baseload power, which is effectively this idea of being able to provide most of the sort of energy needs that we would need day to day for powering our homes, our lives, and our businesses. But there would still very much be a place for those other technologies alongside it. So what actually is fusion? Well, it is the process that powers our sun and all stars. This is why we describe fusion as the ultimate energy source. It only happens naturally inside stars. And put very simply, it's all to do with a change in the nucleus of the atom. This is why it's a nuclear energy source. And with fusion, we are actually simply just combining small light atoms, or the nuclei of, until they fuse together and create the next big element up. In the case of sun, the main fuel is hydrogen fusing into helium, and at the same time as this hydrogen fusion inside the sun, we get a release of fusion energy. And there's in fact billions of fusion reactions happening every second inside the sun, converting all of that fusion into the heat and light that then goes out to the rest of the universe. Now, as you can imagine, while this may seem like a simple process, it is very challenging to actually create those conditions for fusion to occur, hence it only naturally happening inside the very core of stars. So what are some of the sort of extreme conditions that might be needed for fusion to occur? Well, first off, we need it to be in the right state of matter, and that is the fourth state of matter known as plasma. This is where we get a superheated gas and the atoms start to ionize, splitting them up with the positive nuclei from the protons and neutrons left, dissociated from the negative electrons that effectively leaves us with a soup of charged particles. Alongside plasma, we need this fuel. I've already mentioned that the sun's main fuel is hydrogen, but you can in fact fuse several more elements than that. You can fuse everything up to iron in the periodic table. Then there's a region of stability, and then beyond that is when you start to undergo nuclear fission, which is just the opposite and taking those larger, heavier atoms, splitting them apart and releasing energy as a result that way. But these on the screen now are the three key extreme conditions needed for fusion to occur. The first is extreme temperatures. Inside the sun, the core can reach up to 15 million degrees, just a little bit toastier than our ovens. And it's also needs to be very dense inside this as well. It gets up to about 150 times the density of water. And taken together, these result in a very extreme pressure of about 200 billion bar. For those that might not be too au fait with some comparisons, if you were to head outside, we would be experiencing about 1 bar or 1 atmosphere of pressure. The highest pressure on the Earth's surface is deep in the Mariana Trench, which it's up to about 1,000 bar. Highest pressure anywhere on Earth is in our own planet's core, reaching about 3 million bar. So the sun is literally hundreds of billions of times greater pressure than that of our own planet's core. So this really gives you that sort of impression of how challenging it might be to actually recreate this fusion process for us to harness. Why does it need to be so extreme? Well, it's because it is actually quite a complicated process. And even in the sun, while I mentioned that it is just hydrogen fusing into helium, there is a multi-stage process involved with this. And the real sort of crux of the issue is to overcome the force of electrostatic repulsion. So while I said that we need them to be in a plasma state, that also poses the challenge of the repulsive force of having like charges. Like the same ends of a magnet, we have positive nuclei that want to repel and push away from each other. So to overcome that repulsive force, we actually need to input these extreme conditions until we get to a point where we can actually start getting interactions with the strong nuclear force to do that final bit of attraction to really bring the atoms together and allow fusion to occur, releasing all of that energy. So that's how fusion happens in the sun. And at UKAEA, our mission is really all about trying to recreate this process and deliver sustainable fusion energy so that it can power the grid, provide that baseload power. And while we're at it, on that journey, we actually do recognize that there's a lot of extra benefits that can come from it, both in terms of science for sort of plasma physics, but in other sectors as well. And as part of this, we very much see there to be a societal and economic benefit, an impact that we want to have out of our work, particularly as a publicly funded national laboratory. So where is the work that we do? Well, actually nowadays we, as an organisation, have two sites. Our main site is in Oxfordshire at the Culham Science Centre, just sort of between Oxford and Reading. And we have a new site in South Yorkshire, just on the outskirts of Sheffield, at the Advanced Manufacturing Park there. And while we have a significant presence at both sites, it's actually not just us. We're in good company with a lot of other science and innovation groups at the South Yorkshire site. I mean, there's now there's Boeing, there's McLaren and Rolls-Royce and various other organizations looking at kind of like core manufacturing. And then at Culham, we have lots of different organizations. Reaction Engines looks at air-breathing rocket technology. We have a neuroscience organization, Neurobio, coming in. So perhaps off the back of this talk, there may even be some other people that might want to come and talk to you about their different research that's going on. But focusing in on our main site at Culham, and tonight I'm going to focus on our main machine and talking about the core fusion project, but I will also mention an overview of some of the other facilities that we do and the sort of research that we undertake. So we have actually a robotics facility called RACE, and this is looking at how we can actually maintain and upgrade our fusion machines. We have MRF, which is a materials research facility looking at developing cutting-edge materials science. We have OAS, which is actually an apprentice training center, because we need the next generation of engineers and scientists to be coming into this industry, particularly given the kind of long-term view we're taking. And then we have our core fusion projects themselves. So I'm going to be focusing quite a bit on JET tonight. I'm sure several of you might have heard about this. JET is the Joint European Torus, and in fact, the world's largest operating fusion machine. It's quite an achievement, that, because there are over 100 out there. And in fact, one of the other ones is also on our site, called MASCOT Upgrade. And this is in fact a newer fusion design based on that of JET. And because it's newer, the technology is more advanced and may even be a blueprint for us to build the first prototype fusion power plants, of which STEP, that final blue ringed circle, or the two of them there. This is a very new project for us, where we are actually looking to already work on the designs for a fusion power plant that's going to be coming in the next few years. And I'm more than happy to take several questions on timescales and timelines, because I know that's a very common area when it comes to fusion. And in fact, STEP is so new that on the far blue ring, this photo was taken a couple of years ago and the building wasn't even there. So this really is still kind of cutting edge work that we are undertaking to push forward the timeline of having fusion power on the grid. So how are we actually recreating the process? Well, we do a similar reaction in some ways to the sun. We are still fusing hydrogen, but we're fusing isotopes or forms of hydrogen known as deuterium or heavy hydrogen and tritium or super heavy hydrogen. And we call this the DT reaction. And when we fuse deuterium and tritium together, you get helium still made, but you also get a high energy neutron created from this process. And in fact, one of the sort of key areas of research that we're looking at is to develop a technology based on a metal layer known as the lithium blanket, where that high energy neutron will react with our lithium blanket, convert that energy into heat, which then will ultimately be used in the sort of back end of power plant infrastructure to generate electricity. So we're fusing deuterium and tritium to generate high energy neutrons and capture electricity from that. That's the reaction. This is the machine. It is the Tokamak. This is the type of fusion machine that we focus on at UKAEA. The word Tokamak is actually a Russian abbreviation, which translation goes to toroidal chamber with magnetic coils. And it's quite an apt description. The sort of center of this picture, where you see a sort of pink donut ring cloud, that is where the fusion plasma is actually going round the fusion machine and where all of the fusion reactions are occurring. And then around the outside of that pink ring, we have magnetic fields created by two sets of magnetic coils in the blue and the gray rings. So there's the fusion plasma in the center, and then there's our two magnet sets. So we have the toroidal magnets, the blue D-shaped rings. These create a magnetic field going round the center of the plasma itself, creating that toroidal configuration. And then the poloidal coils work to go around the plasma north and south to actually effectively squeeze in the plasma cloud so that it does not actually touch the walls, the inner walls of our vessel. And this really helps to create the confinement. And this really explains the type of fusion that we do. We work on magnetic confinement fusion. There is another type of fusion called inertial fusion, which isn't one that we really focus on here, but there are other groups around the world that are looking into that technology as another alternative that still could well be a viable route to commercial fusion. And then one of the last kind of like core features of the Tokamak is the central column. This is also known as a central solenoid transformer, and some of you will be familiar with transformers. The solenoid is acting as the primary winding, and then the plasma itself becomes a secondary winding, and we are able to generate a current within our fusion plasma using that central transformer column. And in fact, that central transformer column and that current as a result is very key to creating some extreme heat. The heat is so extreme that it actually gets up to 150 million degrees inside jet, over 10 or about 10 times the temperature of the sun. Now, how do we reach that temperature? Well, there's three main mechanisms that we do this. The first is by ohmic or resistive heating, relying on that electric current. And when you can increase current in a system, you can increase the resistance. And as a result of high resistance, you can get high temperature. The next is radio frequency heating. This is well known by the student community because they quite often use microwave dinners, and it works in a very similar way to how a microwave oven would, but rather than using microwaves, we're using radio waves tuned at a frequency to allow the plasma particles to vibrate even more, and thus creating further heat for the system. And then the third and final, and certainly the most complex system, is the neutral beam injection. And this works by actually accelerating some of our fuel as a sort of side product up to high speeds, and then we strip away the charge that's required for the acceleration process so that it becomes neutral and doesn't interfere with the magnet systems already applying. And when those neutral beams fire into the plasma, they collide with it, allowing us to reach that dizzying height of 10 times hotter than the sun. And I'll certainly say that I feel this is the most mind-boggling fact I find of working where I do. The idea that people have been able to create donut-shaped metal box in a random field in Oxfordshire that gets hotter than the sun. In fact, making that metal box not just the hottest place on Earth, but the hottest place in our solar system when switched on and running its experiments. Which brings me very nicely onto JET itself. So I said that I really wanted to kind of like focus on the sort of areas of operation to make JET work, and really get into what is required to run a fusion experiment. JET is a massively collaborative process, and it's been around for quite some time now. It first started running experiments in 1983. And the different areas that I'm going to give you some more detail on. Well, the first is the JET control room, where we actually operate the machine. Then we're going to look at some of the power supplies because, as you can imagine, that getting up to those extreme temperatures and having high magnetic fields in itself does require quite significant amounts of power. We'll also have a little bit more of a look at some of the robotics that actually is being used on JET, and really what spawned all of our sort of newer remote handling work as well. And that is the main robot on JET is called MASCOT, and we'll talk more about that. We'll also just briefly show you some of the things that we have in the assembly hall, which is some important pieces of kit for us to use. And then lastly, we'll actually look at the Torus itself, and really get a feel for what JET is actually all about. Hopefully you can even just see from this picture. I mean, it's easier to get scale when you're in person, but hopefully on this picture you might be able to see some of the sort of vehicles that would be around on the roads, and you get to see that this is a very large piece of kit, and so therefore it is very much a mega engineering project, as well as being very important for the scientific side of our work as well. And there's a lot of interplay and a growing amount or a growing role for engineering within these projects as we scale up towards the delivery of fusion power. So the control room. As I mentioned, this is where we operate JET. As UKAEA, our main function is operators of this fusion machine, and we actually have visiting scientists from labs across Europe and around the world that will come in and effectively have time on our machine as a user, and then they will work with our team of operators to plan and run their experiments to then get the data that they would then go back and analyze and publish in all of the sort of research journals. It broadly splits into sort of two main different types of roles. Again, having this kind of interplay between the more scientific and the engineering sides of this project. Among our operator teams on the scientific side, we have the scientific coordinator, whose role is to work with those visiting scientists and almost acts as a translator to the engineering teams to convey the sort of different parameters that are going to be needed for the scientists to get the data that they're after. There's several other scientific roles, such as a diagnostic coordinator. We have over 100 different types of instrumentation to allow us to measure many different things that are going on inside the fusion vessel, and learn about that plasma in terms of sort of electron density, power output, and there's even microphones. If you were to stand in the control room, you would be able to hear the sound of JET's experiments, and some of the engineers, and particularly the sort of chief engineers that have been around for quite some time, can know precisely how good or bad a fusion experiment on JET might have been just from hearing the audio that gets piped into the control room when an experiment is running live. And the sort of key engineering role is actually on the end of this main control desk, known as the EIC, or the engineer in charge. They're largely in charge of two overall safety areas. One is safety of people, as you would expect, but the other is also safety of the machine itself. So a challenge that we have is with the science that we're wanting to achieve, it's always wanting to be pushing the boundaries of what we know. And so therefore, it's almost certainly wanting to push the limits of JET, perhaps beyond its limits. And so therefore, it's the role of the engineer in charge and the other teams to kind of like find a compromise where we can still be pushing the boundaries of what we currently know, but still allow us to have a machine to work on for even more experiments in the future. There's many other engineering roles. Many of them are involved with the heating systems. So we have a team for the neutral beams. We have a team for the radio frequency heating. There is a power supplies team, whose role is very much to work with the national grid, in fact, as well. So much so that there is a direct phone line within the control room and the power supplies team of JET to communicate with the national grid and actually coordinate the experiments that we're running on JET with the power consumption of the rest of the country. And that is because we draw a lot of power from the grid. We actually use 2% of the UK energy supply every time we run an experiment on JET. So 1% of that, half of it, comes directly from the grid itself. We're one of 10 customers to the UK supergrid, which is the very high voltage connection. And alongside that, to ease our pressure on the grid, despite still taking 1%, we actually store half of the energy when we're not running experiments in giant flywheels just behind the main building where JET is housed. And these are basically big circular concrete slabs that are buried just beneath the sort of ground level. And they can draw energy from the grid when the machine's not running experiments to speed up and store that energy. And then when it's ready to run an experiment, we can release the energy from those flywheels, drain it, and use it to further power the systems that we require. So MASCOT and remote handling is very key to our operations, and even more also for some of the machines that we're looking to develop from Fusion. It is a robot, or specifically a remote handling tool. It's not completely autonomous, and I'll show you the sort of system that we use in terms of a person in the loop type mechanism. But effectively, this is our MASCOT. It's got 2 arms coming down, and it's got grippers for hands, and it's got a whole selection of camera views as well, both on the kind of headpiece, also along the arms, and various other bits around the body too. And these are very important because they actually allow the operators who are controlling MASCOT to be able to see what MASCOT is seeing within the vessel. MASCOT's role is to carry out a whole set of different maintenance and upgrade tasks. And to do that, it needs different tools. So you can see the first picture is just up close and more detail of that sort of basic gripper mechanism. And then attaching to that, there could be everything as simple as a sort of bolt runner or a screwdriver to a very complex bespoke design tile carrier, because the vessel itself, as you can see from my virtual background, is made up of many different metal tiles, and it could be MASCOT's role to take on and off some of these tiles when it's doing its repairs. And then my personal favorite is in fact a pair of pliers that the remote handling team have simply stuck onto a gripper adapter and do actually use in some of the tasks that they need. So I do quite like this concept in showing that you don't always need to over-engineer everything. But MASCOT can go inside almost every part of JET. So it is the manipulator on the end. The pit that you see in the picture is MASCOT. The rest of it that's kind of helping MASCOT to get in is an articulated boom, which actually allows it to reach almost every part of that the main jet vessel itself. And that really does give us the flexibility to do pretty much every task that we might need remotely. There is very rare instances these days where there may be an issue where MASCOT can't reach that element to repair, and that is at a time when we may actually need to gear up a person to go in and do whatever task is needed, but we try and reduce that as much as possible, primarily for safety reasons in terms of the radioactivity that we do get from tritium. And I will outline some of the sort of advantages of fusion, but it does produce some radioactive waste, far less than there is from fission, and that is one we see it still very much as advantageous over the current technology that we've got. But just to finish off MASCOT, this is a picture of Rory, one of our remote handling controllers for MASCOT, and he would be there to actually control a similar mock-up of the arms and grippers that MASCOT would have. And this is what we mean by that person in a loop system. So every movement that the operator for MASCOT would make is copied exactly by Jet in the vessel. And it's not fully coded, it's not autonomous. We believe that actually there is still a very key role for people to play in terms of fast response and accuracy and meeting tasks that haven't been thought of before, and so therefore couldn't necessarily have been predicted through some of the sort of coding, even with the advances in artificial intelligence these days. However, there are some systems that our wider race department is looking at in terms of using AI in more ways. Within the sort of core facility of Jet, there are even different parts to the main building. This is a picture of our assembly hall, where, as the name would suggest, we assemble various different parts before we move it into the Torus hall where Jet is actually housed. It's an ever-changing set of projects that are going on inside the assembly hall, bar one. If you kind of see within sort of in front of the sort of main part of this picture, where you have a kind of curved bulge, this is actually a full-scale mock-up of the main vessel of Jet, or at least one section of it. Jet is made up of 8 segments known as octants, and what you can see in front is the 9th octant. This was a spare piece of Jet that we got in the early days of its development, and weren't ever sure whether we were going to need it. And actually we were able to repurpose this into a training vessel. And so this whole feature is known as the IVTF, or in-vessel training facility. And this is just a little bit of a look inside our IVTF, and you can see that it actually looks much more sort of stripped down, but it still has that kind of characteristic toroidal shape and gives you that sense of being within the vessel itself. It is to scale 1:1. And that therefore makes it a very useful training module, particularly for training our MASCOT operators to do any different tasks that they might need to sort of prepare for inside the IVTF first before they go on to do it inside Jet. And there's many different training tasks for the operators, and it's at least 100 hours of training is required on MASCOT before they let you go and actually do any of the core operations inside Jet. And so then going from the assembly hall, this is just a refresh of the sort of basic component of the tokamak. You've got that main toroidal vessel. In orange above and below are the poloidal coils, and then in white, not very highlighted, are the toroidal coils. Those two magnetic coil sets working together to confine our plasma. And this is the real heart of our operations, and this is JET. So on one side, you get to see the external view, and on the other, you're seeing the internal of the core vessel itself with, in fact, a plasma overlaid. On the external view, you can see that it is a very complicated machine. Many different parts are required for it. In the very corner, just sort of half in shot, half cut out, is sort of the edge of the tower for one of our neutral beams. The neutral beam injectors actually scale up to the whole top of JET, which gets up to about 12 meters high. You can see in yellow potentially these Python cranes. There's 4 of them. These were actually used in the early days of JET's build to move full segments of JET around and do various lifts for some of the other smaller parts. Nowadays, they're actually non-functional because JET has been an ever-evolving project. And with that, we have added many different things, primarily more and more diagnostics. And that really is kind of like the sort of key experiments that we have been testing. We've been sort of adding different elements to allow us to test new measurements on JET for us to sort of further our understanding of the plasma physics and how to make fusion more stable and more efficient, and therefore be able to produce more energy for longer. Now, moving on to the kind of like core vessel itself in that other picture, I've already mentioned that, yes, you can see that it's made up of many different metal tiles. Metals involved are tungsten and beryllium. We use these because they have high melting points, and even though we're not worried about needing materials that can withstand 150 million degrees by the edge of the plasma, it may be down to the low hundreds or maybe even 1,000 or so, and so it is still to high temperatures for enough for us to be thinking about the materials that we are using. And just finishing the section off really, so on that far side of that picture is a real image of our plasma. We haven't photoshopped it. This is a visible light output from one of our diagnostics from a DT plasma. We call our experiments a pulse every time we run because we run pulsed power. We don't run continuous power at this point. That is what we're working towards for full-scale power plants. But with every pulse, we can actually still get a very considerable amount of data out of it. So despite JET's age, it is still giving us some cutting-edge results coming through. So how do we get from JET to a power plant? And how do we really scale up to full-scale fusion power? I've already kind of like hinted somewhat at this. We are very much kind of like trying to just focus on the front end of power plant design, really looking at how we can make fusion reactors to generate energy, which will then generate the heat we need to boil steam, turn it into gas, which then allows us to pass it through a turbine on a generator and up onto the grid, providing electricity. Now, it's that lithium blanket that is going to wrap around the main part of the vessel, and the neutrons will fly out of that, colliding with lithium, having a chemical reaction to produce heat and create the steam and therefore ultimately the electricity that we're looking at. And the lithium also has quite a useful secondary benefit to us that I'm more than happy to go into more detail later with the questions. But JET really is producing these key scientific results, and here's our proof, if you like. Even earlier this year, some of you may have seen in the news that JET had a very significant result. We broke a world record for fusion energy output, and the sort of crux of this result was about being able to produce a high power fusion pulse for a sustained amount of time. As I know some of the people in this audience like to get into a little bit more of the detail, I will try my best to show you some of that. And here we have actually our previous world record that we had for JET. This was achieved in 1997, where we got up to around 16 megawatts of fusion power produced. And more significantly was actually the ratio of power output versus power input. The input for this pulse in 97 was about 25 megawatts. And so we actually got a Q ratio, a power ratio of about 65%. And at the time, that was incredibly significant. And in fact, that still stands today as being a world record, still standing as the highest amount of power produced on JET. But it wasn't sustained. So it was just touched. For the full scale development, we need to obviously actually be getting to continuous power. Now, in 97, we managed to achieve a much lower level of Q, but we did manage to sustain it at around sort of 5 megawatts or 22 megajoules in this case for around 5 seconds. The latest result smashed that record and almost trebled it, really. And really, we were able to get 59 megajoules of power for about 5 seconds. And while this may still sound small to some, what this really proved is that actually we can get high power fusion for a sustained amount of time. And really, we're now focusing on it as an engineering challenge to scale this up, to be able to get even greater power, improve that Q factor, and further improve the length of time that we can sustain fusion. And we're going to try and achieve this with the next big fusion project called ITER. Now, this is a truly international project, currently near the end of construction outside Marseille or Cadarache in the south of France. And the big goal of ITER is to prove that commercial viability and really get a much higher amount of fusion power out than what is actually being put in to run it. What is it that we're aiming for specifically with ITER? Well, really, it's kind of again split into two features. One is a Q factor of 10. So this is that commercial viability touch point of being able to get 10 times greater power output than what is actually being put in and producing net power. And we would achieve that for around 300 seconds is the current aim. But there is also that record to try and sustain high power, and that would be going for a record of over an hour for a pulsed fusion experiment, but at a much lower Q, this time of around sort of 5, resulting in around 300 megawatts. And even though that's lower than the kind of touch point and the shorter pulse, that is still being touted as a very good milestone to achieve in terms of the sort of roadmap that we need to be working towards. But it isn't the end of the story. Really, the end of the story is to go from ITER towards one of the designs that we're involved with called DEMO. So DEMO stands for the Demonstration Fusion Power Plant, and it is part of our European roadmap to make fusion power viable. And it will be a prototype fusion power plant placed somewhere in Europe by around the 2050s. So this project is still some way off. There are a significant number of engineering challenges that are still remaining to be faced. And we get it. We know that fusion is still taking a long time, but we still believe that it is very much still possible. JED has been improving results. Other fusion machines have been helping us to get there, but there do keep coming up new challenges. And that is not particularly surprising when you really think about what we're actually trying to achieve. But hopefully, I would hope that some of you still very much believes that it is worth it for the sort of payoff that we could get from fusion. And then in parallel to that roadmap, which is both kind of like focusing on the jet ETA demo model of the conventional toroidal tokamak, we are also still looking at this parallel route based on a spherical tokamak. And this is where our other machine, MAST upgrade, comes in. So this time, rather than being fully toroidal and ring shaped, we have squashed the machine down and it is more ball or spherical shaped, and we described it a bit like a chord apple this time. So it's still got the central column filling in the middle. MAST upgrade is based on some of the technology that we pioneered as UKAEA from 1999. The precursor to this machine was a machine called START, the small tight aspect spherical tokamak. The spherical tokamak. No, the small tight aspect ratio tokamak is START. MAST stands for the mega amp spherical tokamak. We have a lot of acronyms at our organization, a bit hard to keep up occasionally. But the sort of latest cutting edge work being focused on MAST upgrade is focused around plasma stability, particularly looking at the elements of a tokamak known as the diverter regions. So on MAST upgrade, we have two diverter regions, one on the top and one on the bottom. These are effectively exhaust systems where we can funnel down some of the excess heat that might get produced, but also waste byproducts such as helium or possibly even unreacted fuels to help reduce the sort of number of impurities that may build up in a fusion reactor, and therefore improve the efficiency, and particularly looking to solve one of the issues that we have, which are known as disruptions. These are where the plasma becomes so unstable that it actually touches a part of the wall and then effectively switches itself off, cooling down from a plasma back into a gas, and not very great for that sustained fusion power. And the sort of key technology that MAST upgrade is looking at is a new diverter design known as the Super X diverter. It's a different configuration to some of the previous machines we've had that have been more kind of like just a dump trench. That's in fact what JET has at the bottom of its machine. It's only got one diverter on the bottom. With MAST upgrade in this image, you can see that we've actually kind of like curved the bottom of the machine. So we're actually taking a more sort of gentle approach to taking the excess heat load that might be impacting the bottom of that diverter. And in fact, last summer, we switched on MAST upgrade for the first time, or not switched on for the first time, but we got some of our first key results for the Super X that was proving that it already would reduce the heat load experienced in those regions by 10 times. And that means that we wouldn't have to go in and replace the diverter as frequently when we scale these machines up. So we're constantly now thinking about how we can create longer lifetime fusion machines as well. And really, this leads on to that new project that we're having a much greater focus on called STEP. This is the spherical tokamak for energy production this time. And it's taking that spherical tokamak technology and jumping to the prototype power plant version of this design. Now with STEP, this is much more of a sort of UK project, and we got £220 million from the government in 2018 for the early concept design phase. And the timescale of this is very ambitious. we are looking to get STEP operational by 2040. So actually 18 years away from now. So you can certainly keep that as a mind, as a thing in mind for the current estimate of when fusion power might be coming to the UK. So that's really kind of like the core fusion projects that we're looking at. But to just give a little bit more detail to finish this part of the session off on some of our other facilities. I've mentioned RACE already quite a bit. It's really spun out of all of that work with MASCOT on JET, and it stands for Remote Applications in Challenging Environments. Again, very descriptive of the type of work that we're doing in there, and gives you an incentive for some sort of spin-off scientific benefits that might come from this, because it's not just fusion that these kind of remote handling techniques would be useful. They're in wider parts of the nuclear sector, particularly involved with decommissioning projects such as Sellafield and others around the world. But also potentially in driverless car technology. And in fact, our RACE team works closely with a company called Oxbotica on our Column site, where we are a test center for driverless cars. So it's quite interesting working at a site where sometimes I see cars driven around with the driver in the passenger seat. But it's, yeah, it just shows the sort of breadth of work that goes on really where we are. And then from oh yeah, no, just some more projects that are happening at RACE. So in top corner, that's just an overview of the sort of main work hall. We've got glove box technology, where we're using manipulators to interact with materials that might be right in front of us, but there's also possibility for these to be fully remotely controlled, where the glove box manipulator is actually in another part of the country or even the world, but could be controlled using systems anywhere. We have these robots down in the bottom called KUKA robots that are actually got some roles in the work that we're doing for ETA and demo. And a lot of the projects that RACE is involved with are actually looking at how we can incorporate remote handling work into the design of fusion power plants in the future, because it's much easier to design a pipe, for example, that is going to be the right size for the robot that is going to be worked on, that might be doing welding and any maintenance involved with it, rather than not having this incorporated, and you get a very small pipe with a robot that needs to be larger than that can fit in it. So again, we're looking at all of these different areas because we want to look at the sort of full life cycle design. And the sort of last part of RACE's project are viewed by some as the sort of most eye-catching these days. Some of you may have seen this robotic dog. It's the Boston Dynamics Spot dog, developed by a company in America. And we in fact have a couple of these spots now with our RACE team that are doing some of that work in hot robotic sites, looking at surveying sites, nuclear sites, particularly involved with kind of decommissioning, and allowing us to do remote sensor work as well. So yeah, all sorts of work that goes on with RACE. This is just a little bit more about MRF briefly as well. The key role of the MRF, while it is still very much seen as sort of fusion facility, it's in fact got scope to be a larger use of facility for the broader nuclear sector, positioning itself as a site that can handle mid-active samples. So low active samples up to around sort of 150 megabecquerels are ones commonly used by sort of university labs. At Culham, we are not a fully licensed nuclear site like Sellafield or NNL, where they would be working with high active samples. And so instead, we found a niche where we can actually look at these ones that are in between, that are too hot for the universities to work with, but not sort of viable enough for work to be done on them by the fully licensed sites. And again, MRF is a very collaborative project involved with other research labs across the UK, looking at sort of furthering materials science within the nuclear sector. And I always like to highlight this because I think it's quite a good thing that UK does in terms of caring for development of people, particularly the next generation of engineers and scientists that we're going to be needing when we scale up. And that's why a few years back we started an apprentice training program, and now this has only grown. And we also have a very vibrant graduate scheme that is now taking over 50 graduates a year, in fact, into our program, and really is building that kind of like longer term pipeline that we're going to need for these sorts of projects. And so to summarize, I mean, at UK, we really are looking at all of these different areas that are needed for fusion power. Everything from the sort of core research and plasma physics going on with JET, to looking at new, potentially more advanced and efficient designs with ones like MAST upgrade, to the material science, the robotics. We've even got a team dedicated to sort of tritium and fuel handling and how we can deal with that better and also get more efficiency out of the reactions. And then at our South Yorkshire site is where our fusion technology facility is focused on the manufacturing and testing of technology that is going to be needed for all of this. And along with this, we're really developing supply chain as a sector, helping us to get closer towards projects like STEP, and actually getting to our ultimate goal of having fusion power out there on the grid. And I just wanted to take a very final moment before I open up for questions to celebrate a key day that is, in fact, International Women in Engineering Day today. I've been involved with having some university graduates on our site for 2 days, in fact, doing a good course to get them enthused by the work that we're doing. And we need more women in engineering, and these are just some of the key people that I know and actually consider very good friends. Abir works on our STEP team as a development engineer. On the other corner, we have Katie Taylor, who's a project engineer, started on JET and actually came to us with a physics background. And then at the top we have Liam Morgan, who is a design engineer on JET that's been involved with several sort of diagnostics projects, and actually she's even created her own YouTube channel now to try and do more work to engage others and further kind of like promote the roles of science. And there's lots of different types of people that we need. We need more people, we need more diverse people, we need creative and new thoughts to meet the challenges that are still outstanding in this kind of work. And so with that, I'll just leave you with this final slide. If you want to find anything more after tonight, you can email our education team, or you can check us out online on our websites. And we're also more and more active on social media with YouTube and various other platforms as well. Thank you very much. I hope this was interesting.